Hello everyone, myself HARA PRIYAN. In this video, we are going to see about my mini project that I done related to microcontroller, and I used two softwares for this project named Keil and Proteus. Keil is used for programming and to build the file, and Proteus is a simulation software where we can design our circuit schematically. Okay, let's get on with it. The title of my project is Automated Temperature Control System. Before we see the automated temperature control system, we need to see why there occurred a need for this automated temperature control system. Because the temperature control has conquered many of the industrial sector, especially in the industrial plant, where the air is to be cooled in order to maintain the temperature constantly. For this particular temperature concern, cooling fan is turned on manually, so that when the temperature is high, the cooling fan reduces it. It is done manually, so there occurs a need for an automated temperature control system to control the fan in industries. We can turn on or off according to the temperature in the environment of the industrial plant. Okay. The project objective. The main objective of this automated temperature control system is to provide solution for the industries in the area of their heat concern and or temperature. By using this system, the temperature maintenance will be automated, so there will be less labor effect or no labor effect for the temperature maintenance. The temperature is recorded at the environment, and if the temperature is sensed less or high than the required degrees, the fan is automatically made to turn on or off. By this way, our heat concern is no more a problem. And social relevancy. The automated temperature control system is useful for the industries where temperature maintenance is essential. Like in the food industries or beverage industries. In beverage industries, the temperature decides the quality of the final product, and it can also be used in the steel industry and metal processing industries. In such areas of temperature maintenance, the automated temperature controlled system provides a better solution. And let's see the principle. The project works on the principle of analog to digital conversion. The analog data from the LM35 temperature sensor is given to the ADC 0804, which is an 8-bit microprocessor analog to digital converter. The analog output of this temperature sensor will vary at 10 millivolt per degree Celsius. Why we use this ADC 0804? It is an 8-bit ADC. For any reference voltage of 5 volt, we will get a resolution of 20 millivolt. This is a minimum change in the analog value from the LM35 sensor, which is recognizable. So we use this ADC 0804 analog to digital converter. As per the changes in temperature, the output of ADC is generated. The digital output of the ADC is given to microcontroller, so that the fan is made to turn on or off accordingly. And the components required. First, we see the hardware requirement. In the microcontroller section, there is a 8051 microcontroller, which is an 8-bit microcontroller, AT89C51, and we need a crystal oscillator and ceramic capacitor and 10 kilo ohm resistor and electrolytic capacitor, push button, and 16x2 LCD display to display the output. And a temperature sensor. LM35 is a temperature sensor, and as we told, ADC is an 8-bit microprocessor, analog to digital converter, and we need ceramic capacitor and a resistor pack and 10 kilo ohm resistor one. And in the load section, we need an NPN transistor and a diode, a relay, and an exhaust fan, as we can see in this picture. And software requirements. As I told, we use two softwares, Keil and Proteus. Keil Uvision software makes C compilers, macro assemblers, real-time kernels, simulators, and for 8051 and for 8051 microcontrollers and 8052 microcontrollers, we will get an evolution board so that we can check the program stepwise. And programming language, for this we need to know an embedded C language. And last is Proteus, which we use for simulation. Here you can see it is an actual prototype for an automated temperature control system, where we have an LCD display which displays the output temperature of the output temperature in that particular environment, and an exhaust fan which is made turn on or off, and then microcontroller. These are the websites and journal paper I used to refer to design an automatic temperature control system. Okay, now we all have an idea about what is meant by automated temperature control system. Now here we are going to see what actually happens in the circuit, and also the source program which we will develop and build in Keil software, and we'll see the simulation. First of all, what happens in the circuit? There are four major parts in this circuit. First one is 16x2 LCD display. This 16x2 LCD display is used to display the temperature at the environment, and to display the status of the exhaust fan, which whether it is turned on or off. And then 8051 microcontroller or 8052 microcontroller, and then ADC C0804 IC, which is an analog to digital converter, which converts the analog output fed by the LM35 sensor into digital output, in which the digital output is given to microcontroller to display it on the 16x2 LCD display. Now we can see what is an LM35 temperature sensor. It is nothing but a temperature sensor whose output voltage is linearly proportional to Celsius temperature. The LM35 sensor is already calibrated, so there is no requirement for external calibration. It outputs 10 millivolt for each degree of Celsius temperature. LM35 sensor produces voltage corresponding to the temperature around in the environment or the surroundings. This temperature is converted into an ASCII form, which is suitable for displaying. The ASCII forms are fed into the 16x2 by the microcontroller, and so we can see the temperature at any time on the LCD display. Now let's see the source code. As we said, we need embedded C for this project. We have many variables that makes this analog to digital converter to work. Now first we will see some explanation of this code. For 16x2 LCD interfacing with 8051 microcontroller, we have to define pins first of all, in which a 16x2 LCD is directly connected to 8051. Here we mention S bit RS, RW, EN are the pins of the LCD display. RS is equal to P2 power 0, which means it is RS is connected to the port 2 0th pin, RW is connected to port 2 first pin, enable is connected to port 2 second pin in the 8051 microcontroller. This is for LCD interfacing. For the ADC interfacing with the 8051, we also have the pins called RD, WR, INTR. RD is connected to port 2 5th pin, WR is connected to port 2 4th pin, INTR is connected to port 2 3rd pin. Now we have numerous functions which are used to define the program. For example, we have you see, we can see void ms delay. Ms delay is an delay program used to create a specified time delay. And for example, LCD CMD. LCD CMD is nothing but LCD command. It is a command function which is used to send commands to 16x2 LCD display. And we have LCD convert, LCD INT, LCD data, which continuously displays the data that is coming to the LCD. And void display. We have a display function and an LCD convert function. Void convert. Here there is void convert function. Void convert function is used to convert the ADC data into temperature and display it on the 16x2 LCD display. And we also have an update because temperature won't stay constant. After this void convert, we will go through void update, so that the temperature updated will be again go through the loop of void convert. You see, we can see the same codes down on void update. Okay, let's see, let us just get some parts of the code alone. Okay, we'll start with the LCD command. Here you see LCD command. LCD command, in this part of the code, we are sending the commands. As we said, LCD command is a command function. We are sending commands to the 16x2 LCD display. They are copied to port 2 of microcontroller. Here we made RS is equal to 0, which means that RS is made low for the command write. Enable is equal to 1, which means a high to low pulse is applied on enable pin to start command write operation. And we can see an LCD data. Okay, LCD data. In this part of code, we are sending data to the 16x2 display. The data value is copied to the L data variable. The data value is copied to L data variable, and RS is made high for write operation, and enable is equal to 1, which means high to low pulse is applied on enable pin to start command write operation. And as the same, we have a void convert, and these are the set of formulas that that involves in the conversion of temperature difference into millivolt conversion. And in this void convert loop, we are converting the digital data into temperature and displaying it on the 16x2 LCD display. As we said, update. After the convert program, we have to update the temperature. So this loop is for updating the temperature that comes after displaying first set of data in the LCD. So now we have seen the source code. Now we just open Keil to run the program. So first go to project and open new microcontroller project and give a new name. I just name it as automatic temperature control, and I will just save it. And it would ask for microchip. Which device? You just type microchip and select the microcontroller you want. In this case, I take so I just took a microcontroller that I want. We have seen the source code. Now I will just paste it here. So this is the source code for this project. It is in a text file. We have to save it as a C program file. Now I just save it. as a C program file. .C. Now it became as a C program file, but it didn't come under this project. So you just add this file to the source code. So you have to just search temperature control .c. You have to mention which type of file it is, otherwise it will just add the file as just a test document. So now I have added, you can see here, automatic temperature control.c is added in a target 1. Now we just built, you can see project build time elapsed, no 0 errors and 0 warnings, which means it is good to go. But there is no hex file. Proteus requires hex file for simulation, so we just make this as a hex file. You go to the target and options for target 1 and go to output and create hex file and click OK and build the program. Now see creating hex file from, so you can see the hex file will be created and there is no errors or warning. So now it's good to go. We will go to Proteus simulation now. If you open Proteus, it would be like this. You just enter schematic capture mode. It would take time. First this will be the schematic capture mode in Proteus. First you have to pick all the devices that you want. First I will click on the devices I want. First ADC, I need an ADC, so I'll go with that. ADC 0804. It is an 8-bit microprocessor. You double click it so that you the picked file will be appeared here. Okay, we will go to next one. We needed a silicon resistor, so I choose this silicon rectifier and maximum peak inverse voltage 400 volt. Next on microcontroller, you can see 8D89C5. I chose my microcontroller and now for a button. Button is okay. Oh, crystal oscillator, crystal. Just click that. And a battery, so you add a cell. Next is a capacitor, which is yeah, here it is a non-electrolytic capacitor. LM0167, sorry, 16L I think. It is an 16x2 alphanumeric LCD display, as you can see in this figure. I chosen that. Now we need a temperature sensor, LM35. We'll get an choose this precision centigrade temperature sensor and MOSFET 30 and opto-isolators and a motor, which means a fan, a simple DC motor, and we want to have an NPN transistor, so it is given as octocoupler NPN. Sorry, spelling. Octocoupler NPN. And a resistor. And an SPDT. It is an interactive latched action switch and a normal switch. And yet we need one object, I think so. Tip 1. Now we have selected all the requirements we need, and we don't need to select ground, wire and power connection every time, because you can see now. First we will take this microcontroller, and you have to double click here in the screen. So there appeared a microcontroller, and you just place this wherever you want, and you just place an ADC here. Okay, I need it. Okay, now it is good to go. You just okay. Now we just just place the LCD screen. Sorry. Place the LCD screen somewhere here. Okay, just place upside, and resistor. Just place it here, and the motor. And just place the motor here, and I think switch tip octocoupler. Okay, just we make the connections first. Now you can see I just made all the connections. First the LCD is connect the data pin. The input data pins are connected to the 8052 microcontroller, and the ADC is also connected to the directly to the microcontroller. And this is not a real-time use. We just simulating it, so we have to manually add up the temperature or increase or decrease in the temperature sensor. And this is the motor, which is nothing but the fan, brushless DC motor. It will run. We have this project is mainly for some suitable requirements. As we don't have that requirements now, I just made it that if it increased over the temperature is increased over 30 or more than 36, the fan is made to run, uh, which means the fan will start to rotate. That's it. First, before that, we have to load the hex file into the microcontroller. We just made the connection. We have to load the hex file. Just double tap it. I already uploaded the hex file we have created just now before in Keil software. I just uploaded it in here. If you forget to upload this hex file, the program won't work. I just click OK because I have already updated, and I just debug all the errors. Now I just here the temperature is already more than 30, so just I will play it, then see the fan will be running or not. Okay, display mode. So it will display the temperature first and the fan on. So let's see, the fan will be rotating. So now the fan is rotating. It is rotating in the low speed because it is a simple brushless DC motor fan. So it is rotating at low speed. For industrial purpose, we use other type of fans, other type of exhaust, big exhaust fans, which will require more than 8051 microcontroller, because it requires 80 MGA 8 Atmeca 8 microcontroller. There in industrial purpose we won't use this 8051 because of the current and because of low load, something like that. And see, the temperature is displayed on a LCD screen, temperature 37, and fan is on, and the fan is made to run. You can see that here. Okay, hope this is useful to all of you, and sorry for the trouble. Sorry for the trouble if there is something in the audio or in video. Okay, thanks for watching this.